Hey guys, welcome to your favorite channel, Subhra the Geek. I am your host, I am your host, Subhra. Guys, I am very sorry, I am extremely sorry that in the past 2 weeks there were no videos at all because I and Debayan both were busy in our private lives doing some work. So, first of all, sorry for that, guys. I along with my great friend Debayan, have designed this series for you guys to help you guys understand each and every minute details of the series and of the industry. So these are the series which are catered to the industries, which according to the industry what the industry requires actually. And these are the series which we have planned for you guys. So guys, if you face any problem during the course of your journey, we have linked our Discord server, exclusive Discord server, down below. You can find us, me and Deban over there. Our informations are also given down below, so do check out. And I will link up the series on the I button over there. Each and every series over here, the I button will be over here, and each and every series you can find over there. No issues whatsoever. So guys, today we'll be talking about data distribution. It is one of the fundamental things in statistics, and statistics, as you know, is one of the founding legs of machine learning. And machine learning is the sexiest job of 21st century according to Harvard Business School. So guys, without further ado, I am your host Subhra. Welcome to Subhra the Geek, and along me is,
Debayan.
let's start, shall we? So Debayan, today we are going to talk about different distributions of data. So could you give us a brief about it before we move to your tab?
Today we're going to talk about two of the most important distributions, which I think every aspirant in data science and machine learning should be very familiar with. It's the normal distribution and the binomial distribution. These two distributions are important in like in more ways than you can imagine, and it gets like some of the applications that I have been working with at the startup that I work with, uh, like primarily work around this kind of distributions and how you can creatively leverage the implications and the data distribution and the data rules that come when you work with distributions. And we're going to explore those rules, those tricks today in this video.
So guys, without further wasting any time, let's move to the Debayan's tab, where we'll be explaining each and every part in minute details. So let's start, shall we?
So hey guys, so let's start with the normal distribution, shall. So what you see in front of you is the idealized normal distribution. So on the y-axis you have the probability or the probability density. Please note that in mind. That's the probability density, not the probability. And on the x-axis you have some values, right? So this is the x-axis, and you will have normal your values. You have an array of numbers, you have an array of some variable that you want to understand how the data is distributed, what are the ranges, max, mean, and how the data looks like when you plot it. So this is what it might look like. This is the idealist one. And this shape that you see is unimodal, right? Because there is one mode over here, right, which is the number which comes most frequently. That's what you call the mode of the distribution, and it's perfectly symmetric around the center line, which is this line, right? This line, it's perfectly symmetric around this one and this side, right? So this distribution, or whenever a data variable follows this distribution, it has a follows some very strict guidelines about how the data should behave and what are the assumptions and approximations you can make on the data, right? Let's clear up the mathematics behind that. So when we're talking about a data being normally distributed or follows a normal distribution, we use this symbol, right? And we call it's parameterized by the mean and the standard deviation of the data, right? So mu is the mean or the population mean, and sigma is the standard deviation or the population standard deviation. Mean is it generally found in the center, so the normal distribution works along with the center. This is the mean, and the standard deviation determines this markings that you see over here, and these are uniformly placed, and they all have the same distribution. You can see that if you move one times over here, it's mu plus one times sigma. If you move another times, it's mu plus two times sigma, and so on and so forth. So the distribution is can be totally recreated. If you just, if you, even if you do not have the data, you can just create it from the mean and the standard deviation, right? Here's another trick. If you look at the percentages values and how much those range will contain, right? The first range that you see highlighted in this pink, sorry, this orange pink, this color over here, right? This part, it's around 68% always, right? So what this means is that your data point, 68% of your data variables, of your data ranges, will fall in this space of the distribution. If you consider another this violet part as well from both sides, right? What it means is that now 95% of your data points will fall within this range, which is mu plus 2 sigma and mu minus 2 sigma. You can almost see a kind of pattern, right? And then as you go and as you take this green part as well, this means that 99.7%, let me write that down, 99.7% of your data range will fall between mu minus 3 sigma and mu plus 3 sigma, right? So if you just know the mean and the standard deviation of your data point, and if you have seen that the data point, or you can make the assumption that your data point is normally distributed in some aspect, then you can definitely make these claims that 68% or 95% or 99.7% of your data range possibilities or value possibilities will lie between these two max and mean ranges, right? So what do we mean, by these markers, right? Here's a trick. The trick is the possibility. So what is the possibility that your data point will belong to the 68% range, or the 95% range, or 99.7% range? You can see that as it goes along, if your data point has a 0.03% of appearing in the data, that means it's a very anomalous kind of data, wouldn't you say? If you say that, now has another way. If you think that your data point is beyond one sigma deviation or two sigma deviations, you can automatically make the claim that it is like 100. So if it is between mu minus one sigma and mu plus one sigma, that is one standard deviation away from the mean on either side, it means that the data has a 68% chance of appearing. If it is below two standard deviations from either side, it means that it has a 95% chance of appearing, right? If it is beyond that, then that means it has a 5% chance of appearing. Think about that for a while. Your data distribution, just by knowing the mean and the standard deviation, you can approximate how likely is your data point or your test data point from this distribution. This can set up for very interesting use case scenarios where you're talking about in a very simple anomaly detection system, where you say that you have the normal data points and you want to see how abnormal a new data point is given what you have learned about the distribution of the data. If it falls more than two sigma or two standard deviations away from the mean, you can be pretty sure that it is very unlikely. It's almost like, I would say, 0.15, which is 100 minus 99.7, which is 0.3, divide by 2 because there are greens on two sides. So it's 0.15% chance of your data point appearing if it falls below above or beyond two standard sigma deviations. Pretty neat, wouldn't you say? Like, just looking at the data point, you can make those kind of assumptions without even thinking about it. And if I just give you a random number, right? If you just say, okay, I give you a number x, what's the probability of this number being from this distribution? How do you find out of a random number, right? If you just know the sigma and the mu, you can find out the exact percentage of appearing using something called a z-score. And the way that you calculate a z-score is like this, right? You say z-score of your number x is equal to x minus the mean divided by sigma. What this means is how many times worth of standard deviation is it away from the mean, right? Is it one times, is it two times, is it 1.5 times? And based on the z-score, you can find, this is the z-score. So you can see the one over here, this is the z-score. This is two over here, three over here, four over here. Similarly, there is a one over here, minus one, minus two, minus three, minus four. These are the z-scores, right? And this can help you identify how anomalous or likely your data is from the distribution that you are working with. Um, two more things, two more. If that's too much for you, two more things just to cover up this part. If you're talking about percentile, or what is the probability that your number can belong to a certain range in this normal distribution, what you do is something called a p-norm, right? So here's a little r for you. In r, we have a function called p-norm, right? And what you do is that you wanna pass on the value, whatever your value you wanna find. You say that your mean, you give your mean value over here as some, let's say mu, it, let's say, stored in a variable mu, and your standard deviation as something, right? And you automatically get the percentile in which, according to the distribution, it will lie. So you can automatically understand which percentile of your data point belongs to, right? And if you wanna understand what's the cutoff percentage, if you want to do all those marks based thing, when you have what's the minimum cutoff, what's the percentage cutoff you wanna be in, or you wanna find out. So what you do is that you work with something called q norm, right? In order to find the q norm, what you do is that you just do this 100 minus your cutoff percentile, your percentage, whatever your percentile is, and then you just give your mean, whatever your mean is, and your standard deviation, whatever your value is, and it will automatically give you what's your actual cutoff, or cutoff probability of being cut off from the distribution. So these are two R functions that it's very common in the tidyverse, and I thought that it might be very interesting for you. You can find the anomalous in the like the corresponding function in the Python ecosystem. So that's that for the normal distribution, guys. Okay, let's talk about the binomial distribution. Uh, let's start with defining what a Bernoulli, random variable can be, right? So when you're talking about an individual experiment in statistics or in probability, when you talk about these kind of things, when you have an experiment that has only two possible outcomes, right, then you get a binomial distribution. A binomial means there are only two possible values, and you want to understand, given with the number of experiments that you do, what's the chance of getting the probability of something, right? A binomial distribution describes the probability of having exactly k successes in n independent Bernoulli trials with the probability of success p. Let me repeat that once again. It describes the probability of having exactly k successes or k successful results in your trials when you're considering n independent Bernoulli trials, or trials which have only two possible outcomes, with the probability of success p. When you say that the chances of having one specific output is p, then the binomial distribution helps you calculate the probability, right? So the way that you calculate it is like this, right? So the Bernoulli probability is p is equal to p of k into 1 minus p n minus k, right? So this p that you see over here, this is the probability of your desired outcome, right? Whatever that outcome is, you want to say yes and no. If you want to prioritize yes, so the probability of getting yes of that specific output is p over here, right? And the same p is coming over here as well, so two same values. And then n is the number of independent trials, number of trials that you're doing, how many times are you going to do the experiment, that's n. And k is the number of successes you have seen in those n trials, observed in n trials, right? So p of k is technically is like you're doing an exponential on the probability of success, and 1 minus p, you're doing a probability, or you're doing an exponential probability on the probability of failure. 1 minus p is failure if p is probability of success. So p of, so what this means is that it can only be written like this: the probability of getting k successes, or k successful outcomes in n trials, right, is can be also written as like this: nck, where c is the combinatorial output, right? N items given, total n items given k items, right? That's like that. And the probability of k 1 minus, this is the probability of failure, n minus k. This gives you the probability that you will get k success in n trials, and the previous one gives you the probability, also the shortcut of the same thing. So two formulas, same shortcut. right? Now, when do you use a binomial distribution? A binomial distribution, you must ascertain that the trials are independent. That means if you do trial number one, it should not affect the result of trial number two, and so on and so forth, right? Trials are independent. Your n must be predetermined, must be fixed beforehand. You can't have a shifting goalpost over here. So you must know how many times you're going to do the experiment. Otherwise, we can't calculate those two formulas, right? And there must be only, I think this is a no-brainer. There must be only two outcomes. You can't play around with that. It must have two outcomes. That's why it's a binomial distribution, right? And you must also ensure that the probability of success, right, p is the same for every experiment, right? Whether you do trial number one or trial number 500, the probability of success must remain a constant, or you must maintain the condition such that it is not biased, it's not different every time, right? So you must maintain these two. If you have this, only then your binomial distribution stands. So there's an interesting tidbit that I want to share at the end of this video. So we talked about the binomial distribution, right? So in a binomial distribution, what would you say the mean or the standard deviation is? Every distribution should have one, right? At least you would expect. So in a binomial distribution, the mean can be approximated as n into p, right? Where n is the number of trials you have done or prefixed, you have predetermined that, and p is the probability of getting the correct or the expected desirable output, right? So mean is equal to np, and the standard deviation, that is equal to np 1 minus p. So n is the number of trials, p is the probability of getting the desirable outcome, and 1 minus p is the probability of not getting the desirable outcome. Right? There's a bit of a neat rule associated with this. It says that a binomial distribution with at least 10 successes, 10 expected successes, you would say, right? 10 expected successes or desirable outcomes, and 10 expected failures, right? You've done your experiment, you've got at least 10 successes and 10 failures, right? This would resemble very closely to a normal distribution with a mean and standard deviation. Now how does that come into being, right? So it's like this. So if your np, which is your mean, is more than equal to 10, that has to be the minimum, right? Then your n into 1 minus p, or also has to be 1 minus 10. So this comes from here, this comes from here, right? So if this holds, right, the law which is called the success failure rule, right, states that the binomial distribution with a n trials and p chances of getting a success is almost approximately equal to a normal with a mean and standard deviation, where the mean is equal to np and sigma is equal to np 1 minus p, right? So what this implies is a binomial distribution with a sufficient number of trials and observation will begin to look like a normal distribution, and this lends the credibility that if you have a binomial distribution, if you do it at least more than 10 times, or at least get a decent amount of observations and samples in, you can almost try to work with you can almost make it approximate like a normal distribution, and you can apply the rules and the assumptions and all the tricks and tips we learned with normal distribution on that thing. Pretty neat, right? So a normal distribution is always something I like, and I always try to make sure that I tend towards make the data tend towards a normal distribution. If it doesn't, then it's okay. But if it's possible, I will try to approximate as a normal distribution. Then I can do all kinds of cool tricks of probability and probability density with it.
So guys, that was it for the today. Today we learned about normal distribution, binomial distribution, and how we can relate normal distribution to binomial distribution. So that's a great insight which Debayan has provided with his all the knowledge on the industry. So guys, if you feel any problem during your journey, we have an exclusive Discord server ready. Do share this video with all your friends. Do subscribe to my channel. Do give a like if you like the video. And that's all for the day. Thank you for staying with us. I am your host Subhra. With me was
Debayan.
Signing off. Bye bye.